Hello and welcome. In continuation with our previous lecture of non-aqueous solvents, we have discussed about the various types of solvents, in which we have discussed about the classification in terms of protic or aprotic or amphiprotic, acidic, basic solvents and so on. We have also discussed about the leveling effects and differentiating effects of various solvents, wherein we have said that water is a leveling solvent for both acids and bases. Acid, for example, glacial acetic acid is a leveling solvent for bases and differentiating solvent for acids. And similarly, a basic solvent like liquid ammonia is a differentiating solvent for acids. We have studied the strength of various acids in glacial acetic acid and also in ammonia. So, we have studied that for protonic systems, basic solvents are differentiating for bases and acidic solvents are differentiating for acids. We have studied also that a basic solvent has even a greater leveling effect on the strength of acids than water. For example, acetic acid is a weak acid in water but becomes a strong acid in liquid ammonia. So, liquid ammonia is a base, it's a basic solvent, and acetic acid is a weak acid in water, but the moment it is reacted or added to liquid ammonia, it becomes a strong acid because basic solvent levels off the strength of the acid and brings it to the level equivalent to other strong acids like hydrochloric acid or sulfuric acid, which are stronger than acetic acid in water. According to the CADI-LC concept of acids and bases, any substance which enhances the concentration of positively charged ions functions as an acid in the solvent. If we consider this auto-ionization reaction, wherein AB is the solvent, auto-ionizing to give A plus ions and B minus ions, then any substance which is increasing the concentration of A plus ions functions as an acid in the solvent AB, and any substance which is increasing the concentration of B minus ions functions as a base in the solvent AB. If we consider the solvent water, water auto-ionizes to give hydronium ions and hydroxide ions. So, if a solute increases the concentration of hydronium ions in water, that is, if any solute is added to water and it increases the concentration of H plus ions or hydronium ions, then that solute is supposed to be an acid. And if a solute is added to water and it increases the concentration of OH ions, then that solute is supposed to be a base. In case of liquid ammonia or ammonia auto-ionizes to give ammonium ions and amide ions. Ammonium chloride, for example, if it is added as a solute into liquid ammonia, then it increases the concentration of ammonium ions. So, it behaves as an acid in liquid ammonia, and all amide salts like for example soda amide or potassium amide function as strong bases since they increase the concentration of amide ions in ammonia. An example of neutralization reaction in liquid ammonia is wherein ammonium chloride, which is behaving as an acid, and soda amide, which is behaving as a base, react with each other to form the salt sodium chloride, and along with that the solvent ammonia is also being produced, as we can see from this particular reaction. In this way, a titration can be performed between the two, that is between ammonium chloride and soda amide. A titration can be performed in liquid ammonia as a solvent using phenolphthalein as the indicator. Phenolphthalein is an acid-base indicator. This is also called a reaction between an amino acid and an amino base, since they are involving the use of ammonium ions and amide ions. Strong aqueous acids are also strong amino acids. That means those acids which are strong in water are also strong in ammonia. Many weak aqueous acids behave as strong amino acids. That is, those acids which are weak in water are behaving as strong acids in ammonia, and this is because liquid ammonia behaves as a differentiating solvent for acids, and this is a point which we have already discussed and seen in our previous slides. Coming to liquid ammonia as a solvent. Liquid ammonia, as we know, is non-aqueous solvent. Since liquid ammonia is ammonia gas compressed at high pressures and low temperatures, therefore there is absolute exclusion of water in the preparation of liquid ammonia. Hence, it is termed as a non-aqueous solvent. Then we have liquor ammonia, which is ammonia gas simply dissolved in water. So, there is a difference between liquid ammonia and liquor ammonia. The ammonia solution which we generally use in our laboratories for experiments is liquor ammonia. Liquid ammonia is a non-aqueous solvent which is used for specialized reactions. Hence, liquid ammonia is a non-aqueous solvent. The liquid range of liquid ammonia is from minus 78 to minus 33 degrees centigrade. That is, minus 78 degrees centigrade is the freezing point of ammonia, and minus 33 degrees centigrade is the boiling point of liquid ammonia. Now, whatever we will be talking about or discussing about is in relation to liquid ammonia, which is termed as the non-aqueous solvent. In liquid ammonia, reactions have to be carried out at low temperatures and at below minus 33 degrees centigrade. The system has to be absolutely moisture free for carrying out reactions in liquid ammonia. The dielectric constant of liquid ammonia is 23 at minus 33 degrees centigrade. The solubility of iodides is much more due to its high covalency. So, iodides we all know are highly covalent because of their large size and depending upon the periodic properties. So, they are soluble in liquid ammonia. However, highly ionic substances are less soluble in liquid ammonia. Since the hydrogen bond of ammonia is weaker than that of water because of lower polarity, so the aggregation of the solvent is also less. That is, water is a highly aggregated solvent as compared to ammonia. Hence, ammonia exists as a gas at room temperature because of this weak hydrogen bonding, and therefore we all have studied this fact that ammonia is a gas at room temperature, whereas water exists as a liquid at room temperature because of the extent of hydrogen bonding in each of these solvents. Now, the classes of reactions in liquid ammonia which can take place: number 1, acid-base reactions; number 2, precipitation reactions; number 3, complex formation reactions; number 4, redox reactions; and number 5, solvolysis reactions. Coming to the discussion of acid-base reactions, before that we need to know the difference between solvation and solvolysis. Solvolysis is a process where the solvent molecule also breaks up when a solute dissolves in a solvent. That is, both the solute as well as the solvent offer a competing attraction for each other's lattice and break each other's lattice. However, solvation is a process where the solvent molecules do not break up, only the solute breaks and tries to get dissolved into the solvent. So, moving on to the acid-base reactions in liquid ammonia. Ammonium salts function as acids in liquid ammonia, and this is what we have already discussed according to the CADI-LC concept, because it is increasing the concentration of positive ions in liquid ammonia. Amide salts function as bases in liquid ammonia, again according to the CADI-LC concept, and therefore ammonium chloride and sodamide can react with each other to produce sodium chloride along with ammonia. All these reactions which we are studying are taking place in the presence of liquid ammonia as a solvent, because as we know, all reactions need some solvent to take place. So, the reactions which we are studying over here are using liquid ammonia as a solvent, that means absolute exclusion of water. Sodamide is called monoacid ammonobase, since 1 mole of it is required to neutralize 1 mole of the ammono acid. So, the ammono acid is ammonium chloride and sodamide is the ammono base. Coming to the reaction with amides, ammonium chloride reacts with lead imide to produce lead chloride and ammonia is released along with it. This reaction also takes place in liquid ammonia as a solvent. In this case, lead imide is termed as a diacid ammonobase, since 2 moles of the acid, that is ammonium chloride, are required to neutralize 1 mole of the base, which is lead imide. Coming to the reaction with nitrides, ammonium chloride reacts with bismuth nitride to produce bismuth chloride and ammonia. This reaction again takes place in liquid ammonia as the solvent. Bismuth nitride is termed as triacid ammonobase according to the earlier concepts, that 3 moles of ammonium chloride are required to neutralize 1 mole of bismuth nitride in this particular reaction. These neutralization reactions can be followed in liquid ammonia by 3 ways. The first method is titrations using protonic acid base indicators like phenolphthalein. That is simply an acid, that is ammonium chloride, and a base, whether it's lead imide, bismuth nitride, or whether it's sodamide. They can react with each other using phenolphthalein as the indicator. They can be titrated with each other and the endpoint can be studied. Phenolphthalein is an acid base indicator which is colorless in acidic solutions and is basic in alkaline solutions. Another method to follow this neutralization reaction is with the help of conductometric titrations, where conductance is measured upon a titration of the acid and the base, and the values of conductance are plotted wherein they give a V-shaped curve, and the end point is the inflection point where the lowest, and in case of a V, the inflection point takes place. Similarly, these neutralization reactions can also be studied as potentiometric titrations, where changes in potential are recorded when acid base react with each other in liquid ammonia as the non-aqueous solvent, and then these values of potentials are titrated, are recorded and give an S-shaped curve, and the inflection point gives the end point. Phenolphthalein in liquid ammonia will be pink in the presence of amino bases like amides and colorless in the presence of ammonium salts. Ammonium chloride reacts with sodium hydroxide to produce sodium chloride, ammonia and water. This is a reaction between an acid and a base, but this is not a typical neutralization reaction, because in this reaction water is also being formed along with the salt and the solvent. A typical neutralization reaction is where an acid and a base neutralize each other to produce the salt and the solvent in which the reaction is taking place. However, in this particular reaction, along with the salt and the solvent, water is also being produced. So therefore, this cannot be termed as a typical neutralization reaction. Oxides and hydroxides, which are basic in water, are also basic in ammonia, but to a lesser extent. And this is because of the various leveling effects which we have studied earlier. Acids will be further leveled in liquid ammonia. Consider the following reactions. Hydrochloric acid reacting with ammonia, producing ammonium ions and chloride ions. Acetic acid reacting with ammonia, producing ammonium ions and acetate ions. Both of these reactions are being considered to take place in liquid ammonia as the solvent. In both the reactions, the ionization is 100%, showing that the acids are further leveled in liquid ammonia. Urea is a weak base in water, but it behaves as an acid in liquid ammonia, as bases are further differentiated in liquid ammonia. So urea, we all know, is a weak base, but that weak base is existing in water. But actually, when we take urea in liquid ammonia as a solvent, it behaves as an acid. The reaction which is taking place between urea and ammonia in liquid ammonia as a solvent is producing ammonium ions, and along with that NH2CONH minus, and this reaction is proceeding towards completion, showing that it is being differentiated in liquid ammonia. In this, since the concentration of ammonium ions is being enhanced, so urea is behaving as an acid in liquid ammonia, and this is the reason why urea is behaving as an acid. Coming to precipitation reactions, the second class of reactions in liquid ammonia. Most ionic compounds are less soluble in liquid ammonia in contrast to the aqueous medium, and this is because in liquid ammonia is a non-aqueous solvent. All ammonium salts are soluble in liquid ammonia. All nitrates are soluble, and many iodides are also soluble in liquid ammonia. All silver salts are soluble in liquid ammonia because of the formation of the silveramine complex, which is given as the formula AgNH3 whole twice plus. Only sodium ion, ammonium ion and beryllium ion chlorides, or as we say sodium chloride, ammonium chloride and beryllium chlorides, are soluble in liquid ammonia. Rest all chlorides are insoluble. So potassium nitrate on reaction with ammonium chloride produces potassium chloride and ammonium nitrate. Potassium chloride is showing us as a product or a precipitate in this particular reaction, which is used to prepare small quantities of very pure anhydrous salts. Sulfides can also be prepared in liquid ammonia as a solvent, and all these reactions, as we are discussing again and again, that these are taking place in liquid ammonia as the solvent. So ammonium sulfide on reaction with zinc nitrate produces zinc sulfide along with ammonium nitrate. So sulfides can also be prepared in liquid ammonia by this particular reaction which is taking place in liquid ammonia again as the solvent. The trends in solubilities of chloride, bromide, iodide ions is reversed in liquid ammonia as compared to water. That is, in water chlorides are highly soluble, then bromides and then iodides, whereas in liquid ammonia iodides are most soluble, then bromides and then chlorides. And this is evident from the fact that iodides are covalent and hence will be least soluble in water and will be highly soluble in liquid ammonia, which is a non-aqueous solvent. Chloride is most ionic and hence is least soluble in liquid ammonia. Zinc ions react with amide ions to produce zinc amide, which further on excess reaction with amide ions in liquid ammonia as a solvent produces a zinc amide complex. Heavy metal amides can be precipitated in liquid ammonia. So, this is a way in which a heavy metal amide or zinc amide is first precipitated, and then if excess of amide ions are added, then it forms a soluble complex. Also, in excess of liquid ammonia, a soluble amido complex is formed, as we have seen in this particular reaction. The reaction is similar to the reaction in aqueous solution, which can be shown as follows. Zinc ions on reaction with hydroxide ions give zinc hydroxide, which is a precipitate, which on further reaction with hydroxide ions gives zinc 4,2 negative, which is a soluble complex. This particular reaction takes place in water as a solvent, and the previous reaction which we have studied with amide ions takes place in liquid ammonia as the solvent. So, both these reactions are comparable or they are similar. One is taking place in a non-aqueous medium, the other one is taking place in an aqueous medium. This behavior or this reaction illustrates the amphoteric behavior in liquid ammonia. Silver ions on reaction with hydroxide ions give silver hydroxide. This reaction takes place in water as solvent. Silver nitrate reacts with amide ions giving silver amide. This reaction takes place in liquid ammonia as a solvent. Nitrate ions along with mercurous ions and amides give Hg3N2 mercuric nitride along with ammonia and hydroxide ions. All these reactions are precipitation reactions. Silver hydroxide is a precipitate, silver amide is a precipitate, mercuric nitride is a precipitate, which take place in liquid ammonia as the solvent. Many complex formation reactions also take place in liquid ammonia, and many examples can be given for these. Zinc, for example, zinc ion reacts with amide ions to produce zinc amide, which is the precipitate. On further addition of amide ions, it gives zinc NH2,4,2 negative, which is a soluble complex. So, complexes have been formed in both the cases. Zinc amide is also a complex. Zinc amide amido complex, which is zinc NH2,4,2 minus, is also a complex, but it is a soluble complex. So, the amido complex formed here is similar to the hydroxo complex in water. So, this reaction which is taking place in liquid ammonia as a solvent. A similar reaction can take place in water as a solvent, wherein zinc can react with hydroxide ions to produce zinc hydroxide first, and then a soluble zinc hydroxo complex, just exactly similar to the zinc amido complex. Aluminium can react with amide ions to produce aluminium amide complex, and if excess amide ions are present, then a soluble amido complex of aluminium can be formed. All these reactions are taking place in liquid ammonia. Silver can form amine complexes in liquid ammonia upon reaction with amide ions as the reacting agent. Thank you so much.